Symmetry of a graph is important because a lot of functions have symmetry and are symmetric. One that we're very familiar with working through intermediate algebra and algebra 2 is a parabola. We talked a lot about symmetry when we worked with the parabola. So we noticed that it's kind of mirrored, that one side reflects over to the other side. This is an example of symmetry on the y-axis. And the reason for that is because we could fold our graph in half along the y-axis, and it's the same on the left side as it is on the right side. So the y-axis symmetry is when you have a mirrored effect on the left side and the right side. And that's one that we're really familiar with. Here is an example of x-axis symmetry. And that is where it's the same on the top and the bottom. So if I draw a line on my x-axis, it's the same on the top as it is on the bottom. And then our third example of symmetry is called symmetry with respect to the origin. And that's a combination of the two. It's kind of like, instead of having symmetry going straight up and down or straight across, it's right in between those two. It's a combination. So I actually like to think of it as symmetry diagonally through the origin. So it's the same in the first quadrant, right? Because in a graph, we have quadrants. We have quadrant 1, and then we go counterclockwise to quadrant 2, quadrant 3, quadrant 4. So it's the same in those opposite quadrants. And that is a result of a combination between x and y. So like I said, I like to think about it as if you drew a diagonal line, then it's the same in one quadrant as it is in the third quadrant. And knowing the symmetry, if we go back up to the top here where there's kind of an introduction, knowing the symmetry of a graph before you attempt to sketch it is helpful, because then you only need half as many solution points. Like if I know a graph is symmetric to the x-axis, if I know this is true, I could just find all of these points up here, and then I can mirror those points down below. So I would only need to calculate the points up here, and then I would mirror it across the x-axis if I know that it's an x-axis symmetry. So that's one reason that knowing symmetry is helpful. So how do we know if you have symmetry? There's 3 tests on a graph that you can use. So we are going to read through these because it is important that we go through all of them. So a graph is symmetric with respect to the x-axis if wherever you have a point xy on the graph, then x and negative y is also on the graph. So what that means is the x value stays the same, but the y value, the positive version is there and the negative version is there. And then the opposite is true for if you're looking for symmetry with respect to the y-axis. If you have that point xy, then the y value stays the same, but the x value has that negative. So what that means is the y value stays the same, but we flip over from the right side to the left side and it's the same thing. And then with respect to the origin, it's both of those things put together. So if we have x and y, then I'm going to flip both of those values, negative x and negative y, on my graph, which makes sense because we just talked that if you have symmetry with respect to the origin, then it's a combination of x-axis and y-axis symmetry. So if you look at this example, it says you can conclude that the graph of y equals x squared minus 2 is symmetric with respect to the y-axis because the point negative xy is also on the graph. So let's focus in on our points here. Now, I can tell by the graph very visually that if I was given this graph, I know that it's the same on the left and on the right. I know it's flipped across the y-axis, so I know that's y-axis symmetry. So visually, it's easy to see. But if I were only given these ordered pairs, what I can do is pick one, and I would pick one where they're both positive. You don't have to, but it's just easier that way. So if you have an ordered pair that's both positive, so here we have 2 and positive 2. What I would want to look for, because I know this is x and this is y, I would want to look for if you have a 2 and a 2 where either of the signs change. And that would be over here. And if we look here, it's the x value that changes. X value becomes negative. Y value stays. So if your y value stays, whatever value stays the same, that's the symmetry that you have. So this is symmetric to the y-axis. So looking at a graph, it's easy, but we also want to know how can we use a table of values, and that's what you can look for. So if you're not given a graph and you're not given a table of values, there are algebraic tests for symmetry. So this would be if you have no table, no graph, only an equation. So we'll read through what the 3 tests are, and then I took the example from your textbook to give an example of each of these. So first, to check for symmetry to the y-axis, if you replace y with negative y, you get the equivalent, you get your original equation. So equivalent equation would be like your original. So what that means is whether the y value is positive or negative, it is a solution if it's matched up with the same x value. And then the opposite is true for y-axis. So for the y-axis, we're going to keep the y value the same, and we're going to replace x with negative x. And if doing that results in the original or the equivalent equation, then you have symmetry to the y-axis. And then the origin is a combination of the both. If you have an equation symmetric with respect to the origin, then both of those things is true. So replacing x with negative x and y with negative y, you get that original or equivalent equation. And you want to check all 3 of these. And so here's what that looks like. Here they give us the equation y equals 2x to the third. So check it, or test it, it says. Test for symmetry with respect to both axes and the origin. So what that means is you need to do all 3 of those things that were listed above. And here the book has it laid out. So for the x-axis, we replaced y with negative y, and these two are not the same. So those are not, it's not symmetric to the x-axis. For the y-axis, we replace x with negative x. Now, negative x to the third power becomes negative. So now this is not the same as our original. So it's not symmetric to the y. Now you might think, well, if it's not symmetric to the x and it's not symmetric to the y, then how could it be symmetric to the origin? Well, it's not one or the other, remember. Testing for this x-axis symmetry is only for the x-axis. And then same thing with y, it's only for the y. The origin, we do have to show the work through because that is a combination of both. So we're replacing both values. So we're taking our y and making it a negative y, and then our x and making it a negative x. And in this case, we get negative y and we get a negative on the other side. And when you simplify this, right, 2 negatives, I would divide by negative, make it positive, and this is my original equation. Okay, so it is, sorry, it's blurry. That was a copy from the textbook. It is symmetric to the origin. So this one is a yes. So you might be thinking, well, if it's not x and it's not y, how could it be the origin? And that's because it is a different test that we're doing, right? We have to combine the 2 to get the origin, not just take them individually. So it says on the bottom of the 3 tests for symmetry, the only one that's satisfied is for the origin. Then you can see a graph. That's what the graph looks like. So what you can do, a good check on these, is use the app called Desmos, because then you can graph and see what your graph looks like, and you can check your answers that way. And here's one where we have a graph, y equals the absolute value. Good review there. And remember, absolute value is always positive. So if you just kind of read through what they did here in example 7, again, this is straight from the textbook. We make our table, we get all of our ordered pairs, we see what it looks like. And then there is a note down here that this equation fails all 3 types of symmetry. This is not symmetric in any form because it's not symmetric with the y-axis, right? It's like shifted over a little bit. It's not flipped over the x-axis. And it's not symmetric if I draw a diagonal line with the origin. So there are graphs that have no symmetry at all. That is always an option. And then there's a reminder down here too about your absolute value bars, meaning that the y value is always non-negative, so it's always positive.